Since the dawn of the nuclear age, the world has lived under the shadow of the ballistic missile. These are not cruise missiles that fly low, but weapons of mass destruction, launched high into space, arcing across continents at phenomenal speeds. The threat they pose is existential, a matter of minutes between peace and annihilation. But over the past few decades, a new, complex shield has been forged. Ballistic Missile Defense, BMD. This is not a single system, but a layered architecture, a highly sophisticated network of satellites, ground and sea-based sensors, command centers, and supersonic interceptors, all working in concert. This is the story of that shield. We're going deep into the physics, engineering, and tactical genius that makes modern BMD possible. By the end of this film, you'll understand why this is arguably the most challenging defense task in history. Understanding the enemy, the ballistic trajectory. To defeat a ballistic missile, you must understand its flight path. Its trajectory is defined by gravity and momentum, following three distinct phases. 1. The boost phase, the slow burn. This is the initial ignition and acceleration phase. It's the shortest, 3 to 5 minutes, and often the most vulnerable phase. Why it matters? The missile is moving relatively slow and is a bright, infrared beacon due to the hot rocket exhaust. It hasn't deployed any countermeasures yet. Intercepting here is ideal, but requires assets close to the launch site. 2. The midcourse phase, the space coast. The missile engine shuts off, and the re-entry vehicle, RV, carrying the warhead, coasts in the vacuum of space, often reaching altitudes above 1,000 kilometers. Why it matters? This is the longest phase, up to 20 minutes for an Intercontinental Ballistic Missile, or ICBM, offering the defense system the most time to engage. However, this is where the enemy deploys its countermeasures. Decoys, chaff, and fragments, making the real warhead almost impossible to identify instantly. 3. The terminal phase, the final dive. The RV re-enters the Earth's atmosphere, plunging toward the target at speeds, often exceeding Mach 20 times the speed of sound. Why it matters? Atmospheric friction helps weed out lightweight decoys. However, the short time window and extreme speed demand near instantaneous reaction and perfect accuracy. The layered BMD architecture. The defense network operates on the principle of new shoot-look-shoot and a layered defense. No single component is sufficient. A. The eyes in space, infrared warning. The first hint of an attack comes from the space-based infrared system, SBRs. These satellites are positioned in geosynchronous or highly elliptical orbits, constantly scanning the Earth for the massive heat signature of a missile launch. The science. SBIRs uses highly sensitive IR telescopes to detect the specific wavelengths emitted by burning rocket fuel. This early warning buys critical minutes. B. Ground and sea-based tracking radars. Once launched, the target is handed over to specialized ground and sea-based radars. The key player here is the AN-TPY-2 radar. The Science TPY-2 is a mobile, high-resolution X-band radar. X-band frequencies allow for extremely precise imaging, essential for distinguishing the actual warhead from the decoys and debris in the midcourse phase. The sea-based X-band radar, SBX, a massive, floating radar platform used primarily for midcourse discrimination and tracking ICBMs. C. C2BMC, command, control, battle management and communications. C2BMC is the nervous system of the entire defense enterprise. It takes data from every sensor, fuses it, calculates the missile's predicted impact point and optimal intercept location, and assigns the target to the correct interceptor, all in real time. The hard kill, hit-to-kill technology. BMD systems do not rely on conventional explosive warheads. They use kinetic energy interceptors, KIs, AEON technology known as hit-to-kill. The principle. The interceptor carries a small, sophisticated vehicle called a kill vehicle, KV. This KV uses its own onboard sensors, actuators, and guidance system to crash directly into the target warhead. The physics. The impact velocity is staggering, often exceeding 10 kilometers per second, or over Mach 30. The resulting kinetic energy is so immense that it vaporizes both the kill vehicle and the incoming warhead upon impact. The layered system explained. Layer 1, Strategic Defense, ICBMs. GMD, the ground-based midcourse defense GMD system, is the cornerstone of the defense of the US homeland against intercontinental ballistic missiles. ICBMs, the hardware. The ground-based interceptor, GBI, is a huge, multi-stage rocket stationed in silos in Alaska, Fort Greely, and California, Vandenberg Space Force Base. The mission: to intercept the ICBM warhead in the midcourse phase, outside the atmosphere. This is the highest altitude, highest risk interception task. The challenge: discrimination. The GBI's exoatmospheric kill vehicle, EKV, must correctly identify the single warhead among a cloud of possible decoys and debris in the blackness of space. Layer 2, Regional Theater. Defense, MARBMs, IRBMs. A. Aegis BMD and the Standard. Missile 3, SM-3. The platform. Deployed on U.S. Navy Aegis destroyers and cruisers, and increasingly on Aegis ashore sites in places like Romania and Poland. The mission: to defend regional allies against medium and intermediate range ballistic missiles, MRBMs, IRBMs, primarily intercepting in the midcourse phase. The missile, the SM-3, it uses a sophisticated kinetic warhead that operates at extremely high altitudes, extending the defensive umbrella far beyond the ship. B. THAAD, the high-altitude shield. That, Terminal High-Altitude Area Defense, is a highly mobile, ground-based system. The mission: THAAD is designed to hit targets that have survived the upper layers, intercepting them during the high-altitude, terminal phase, right as the warhead begins its plunge back to Earth. The distinction: THAAD's role is to catch the missile outside and at the very top of the atmosphere, often operating as a backup to the Aegis systems. Layer 3, Point Defense, SRBMs, Patriot Fur, short-range threats, and final point defense. We have the legendary Patriot Advanced Capability 3, PAC-3 system. The mission: to defend small, critical areas against short-range ballistic missiles, SRBMs, in the low-altitude terminal phase. The interceptor. The PAC-3 missile is a compact, highly maneuverable, hit-to-kill interceptor, designed to operate inside the dense atmosphere. The science of overcoming the challenges. This is the Gordian knot of BMD. Discrimination. In the vacuum of space, a lightweight balloon decoy and a massive warhead travel at the same speed. They look identical to basic tracking radars. The solution: the key lies in multispectral sensing and X-band precision. X-band radars, like TPY-2, can generate detailed, high-resolution radar images. This allows analysts to look for subtle differences in shape, size, and material density. Wiggle logic. The system might command the radar beam to tickle the objects. Decoys, being lighter and less structurally sound, may wobble or change course slightly under the radar's energy, while the heavy warhead remains stable. The hypersonic threat. A new physics problem. The next frontier of missile defense is the hypersonic weapon. Unlike traditional ballistic missiles, which follow a predictable, parabolic arc, these weapons fly faster, exceeding Mach 5 times the speed of sound. Fly lower, operating in the upper atmosphere, below the typical range of GMD and high-altitude SM-3. Maneuver. They can change direction dramatically, making the predictable tracking models of BMD obsolete. The defense response, HBTSS. The emerging defense concept is tracking layers. Systems like the hypersonic and ballistic tracking space, sensor HBTSS, are being developed, a constellation of LEO satellites designed to maintain constant custody of the fast-moving target and handoff, tracking data seamlessly. Policy, economics, and the future. The economics of the SHIELD BMD is not just a technological challenge, it's an economic one. This is the unfavorable cost-exchange ratio. An enemy can mass-produce simple, relatively cheap ballistic missiles, perhaps $1 million each. This disparity means an attacker can saturate the defense by simply launching more missiles than the defender can afford to shoot down. This economic reality drives the need for multi-layered systems, ensuring the kill vehicle is only launched when the target is definitively identified. Ultimate answer to the cost-exchange ratio and the hypersonic threat may lie in directed energy weapons at DES, laser weapons. High-powered lasers on ships, aircraft, or ground vehicles could potentially destroy missiles in the boost phase. The physics. Lasers travel at the speed of light, providing an instantaneous kill. The cost per shot is incredibly low, essentially the price of the fuel needed to run the generator, turning the cost-exchange ratio dramatically in favor of defense. From tracking a flash of light away to intercepting a projectile traveling 15,000 miles per hour, BMD is a constant race against destructive technology. It is a shield built not of steel, but of light, logic, and relentless velocity. The future of missile defense, the journey of ballistic missile defense is a testament to human ingenuity. It is the most sophisticated peacekeeping apparatus ever conceived, 20,000 miles,